Assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
For this problem, we're told we have a long uniform rod that has a mass of 0.6 kilograms that's free to rotate on a horizontal plane, and that it has a vertical axis through its center. So this is looking from top down at the rod. So there's a vertical axis to the center that allows the rod to oscillate and rotate. Attached to it on one side is a spring that is a constant of 1,850 newtons per meter. So if the rod rotates at a small angle and then releases, we're trying to figure out what will the resulting period be when it is released. So we're going to have to work through and figure out how to put a couple of different equations together in order to solve this problem. So our first equation is force equals negative k times x, where k is our spring constant and x is the spring elongation, so how far the spring will elongate. This first force will exert torque onto the rod, making the rod itself rotate, and torque has the equation negative F times L. Assuming that L is the distance between the center and the end of the rod. So now we can substitute in negative kx for F, and we end up with torque equals negative kx times L. Now, assuming that the angle is small, then we can write the elongation, or x, in terms of the angle. We can take our x here and write it in terms of x equals L theta. So just putting that back into our equation, we end up with torque equals negative k L squared theta. Okay, so we're still not quite there. We still have a couple more iterations we need to go through here. The first being that we have to think about angular acceleration. So for that, we have torque equals inertia times acceleration, and where inertia is the rotational inertia of the rod around its center. So we can now put these two equations together, and we have inertia times acceleration equals negative k L squared theta, and we can solve for acceleration, which equals negative k L squared divided by I times theta. All right, this is still simple harmonic motion, so A actually again can be substituted out, where A equals negative omega squared times theta, and we can then substitute that in for acceleration, and when we simplify, we will end up with the term omega equals the square root of k L squared divided by I. The period can also be written in terms of angular frequency as period equals 2 pi divided by omega, and we can use that as well, so that we end up with the equation period equals 2 pi divided by the square root of KL squared divided by I. And we can rewrite this equation as 2 pi times the square root of I divided by KL squared. All right, next we need to figure out inertia and get it into terms that we are going to be able to work with. And since we have that the length between the center and the end is L, then the length of the full rod is 2L. So we can use that to go ahead and find our inertia using the equation for a rod with a length of 2L rotating about its center. Inertia equals 1/12 the mass times 2L squared, which equals 1/3 mass times L squared. So substituting it up into here and simplifying, we get that the period equals 2 pi times the square root of the mass divided by 3 times the spring constant. We have our mass and our spring constant over here. It was given as our knowns in the problem. So plugging that all in, we have our period equals 2 pi times the square root of 0.600 kilograms divided by 3 times 1850 Newton meters, which gives us a final answer of 0.06533 seconds.